Thank you, James.
Hey.
And we have James himself in the flesh, so to speak, to answer any questions. So while questions are coming in, let me just start by asking, currently, all the verification that you're doing seems to be on a single node. Do you have any idea what it would look like to try to do this reference model on a distributed spec, again, as it can function as your spec?
Yeah, that's a really interesting question that we've thought about a bunch. AWS has written a paper before about how we use TLA plus for distributed protocols. And we've been thinking a lot more about how to incorporate those into this kind of thing. And I think the way that it probably starts is if we can extract these reference models into specifications for the behavior of an individual node and connect those to the protocol proofs that we already do for the distributed system, then we can get at least some level of confidence that the assumptions that our protocol proofs are making about the behavior of each node are actually what we've been checking that each node actually does. So that's kind of the approach we've been chasing at the moment. And then we've also thought a little bit about how we could extend some of these concurrency tools that we have to also reason about distributed systems. So kind of coming at it from the other angle of starting with a single node verification and then adding a second node, let's say, and having them communicate and controlled by a model checker or something like that.
All right, thank you. So let me start picking up also some questions from the audience. There was a live question. I guess the hand has been lowered. So let me actually, Aditya has a live question. Aditya, let me promote you to panelist. You can ask your question live. Again, if you have oh, now I see Sanjit's question as well. All right, let's get Aditya's first and then we'll get to Sanjit.
Yeah, so I'm from UT Austin. Great work, this is super cool. How expandable is your concurrency model to other languages, and is it super dependent on Rust, the Rust underlying specification?
So the concurrency checking that we're doing is based on a lot of work that people have done, including at SOSP and OSDI, on stateless model checking. And so the idea is pretty general. There's some really great tools for C#, for example, that Microsoft has built, called Coyote. There's great tools for Java. Java Pathfinder is pretty good at this stuff. So the general idea is pretty reusable. The specific tool that we built is Rust specific. That's mostly just for convenience for our developers, right? Being able to use a tool that's easy to use and produces nice error messages and debugging hints and that kind of stuff. It's just a little bit hard to specialize if you want to focus on lots of different languages at the same time. So I think the techniques generalize really well. The specific instantiation of the tool is Rust specific, but that's mostly for usability purposes rather than something fundamental.
Okay, thank you.
All right, Sanjit, you want to ask your question?
Yeah, hey James. So I had a question on the language that you use for specifying the reference model. So I know a lot of other work at AWS uses P or TLA plus. Could you go into more of the reasoning behind using Rust as a language, and also like for specification, and also like is that a generalizable thing, or what's the limitations of using Rust for specification?
Yeah, I would say that it's really a pragmatic choice, right? Like if you were to put me on the spot and say, what is the best specification language to use? Like Rust would not be at the top of my list, right? In isolation. The reason we do it is because the implementation code is already in Rust. And so if we have to specify the system that already exists in Rust, and our choice is either we specify it in a different language that our engineers aren't familiar with and they have to go and learn. And there's all these questions about, well, if I wrote the spec like this in TLA plus or in P, does it actually match the semantics in Rust or not? Those kinds of things. So writing it in Rust just makes it a lot easier to maintain and a lot easier to understand for our engineers. The trade-off is that it's not a language that was designed for this, right? So you don't get the nice features that you might get in a modeling language. But as far as choices of implementation languages go, I think, if the system is written in C, for example, I don't think we'd use C as a specification language. It just doesn't have the same set of features, standard library stuff, convenient stuff, honestly, that Rust has. So Rust is not the best specification language, but it is sort of good enough to write down the kinds of specs we want to write.
Thank you. So I guess let's take one more question. And there's a question from Shudong. You want to ask a question, Shudong?
Yes, great work. So I'm curious about the sequence of operation that is a test workload used in the property-based testing. So is that written manually or generated automatically? And if it's like a really automatic generated, how do you actually generate all the sequence of operations and even the input and even consider the dependency between operations?
Yeah, good question. So those are generated automatically, and they're randomized. So we're explicitly not shooting for, did we cover every single possible behavior? Because those tests can be, the example on the slides was like 3 steps, but the actual tests are 100 or 200 steps, right? They're very big. So we're never going to cover that entire space. So what we do have to do is try to be careful about what types of tests they generate. Like there's a lot of symmetry in that space that we perhaps want to try to avoid searching. There's also a lot of edge cases that we want to make sure that we have some coverage of. A common one in a storage system is, if you do writes that are almost page sized, those are things that tend to trip up a storage system, right? They tend to trigger edge cases around the edge of a page. And so we introduce biases into our test generation to try to find cases like that where we're generating tests that are writing around page sized operations. We talk in the paper a bunch about the different kinds of things that we do here to try to bias the search towards what we might call interesting test cases. But the overall answer is, we're explicitly not aiming to cover that entire space. We're trying to cover as many of the interesting tests as we can generate automatically. And that's kind of the overarching goal.
Thank you.
All right. Thank you, James. We're coming right up on time. So thank you. There are actually 2 more interesting questions on Slack. So please continue the discussion on there. And then we'll see you again at the panel at the very end. Thank you for the great talk. All right. So our next speaker, let's move on to the next paper. Our next speaker is Antonio Paolillo. He got his PhD in computer science from the Université Libre de Bruxelles, and forgive me if I butchered that pronunciation. That's in Belgium. He focuses on system research, operating system design, and benchmarking, and he's now working full-time at Huawei in the Dresden Research Center, and he will present the recent work on logs for large NUMA systems. Please play the video.
All right, so we'll now have some time for questions and answers. So first, just a little bit of the logistics here. After each of the 3 talks, we'll have about 8 or 9 minutes for questions and answers about that specific paper. And then at the end, after all the 3 talks, we'll have a 10-minute panel in which you can also ask questions. So if you have a question, either select raise hand in Zoom. And if you do that, we'll promote you to a panelist and you can ask the question live. Or alternately, you can post your question in the appropriate thread in Slack, and then I'll just read those questions off of Slack. So while we're waiting for some audience questions to come in, I have some questions for you already, James. So my first question is, so you talked about using a reference model as a specification, and that's something that's kind of very broad and a very comprehensive specification. And then I saw in one of the figures in your paper, you're also checking some more specific properties. Like one of the figures shows inserting a value and then getting the value and seeing if it's the same. So kind of what's the relationship between those, and what determines which one you use when?
Yeah, that's a really interesting question. I think the short answer is that we don't have a good answer for that particular decision. Some of the things are really easy to check just by, the reference model has some state, and we're just checking some invariant about that state and how it relates to the implementation. But there are some properties where we really care about either the thing that was returned from an implementation method, or potentially some side effects that method had. Like we want to check that an IO was actually executed or it wasn't executed, and properties like that. And those we don't capture in the reference model today. And that's mostly a trade-off of just like trying to keep the reference model simple, right? We could totally equip the reference model with all the knowledge that it needed to do these more complicated checks, but it just make it more and more complex. And so it's kind of a trade-off of what's easy to express in this kind of executable spec style versus what is perhaps more tricky.
And is that complexity just a matter of having too much code, or does it make the tools too difficult to run? Like, do you have state explosions or something if the reference model?
I expect it's a little bit of both. It's certainly like a lot of code. And one of the things we really like about the reference models that we have right now is that they are, in Rust terms, they're implementing the same trait as our implementation, or in Java terms, they're implementing the same interface as our implementation. So we don't have any sort of backdoors into the reference model or anything like that that make them different. And the more that we have to track this more complicated kind of behavior, the more that we have to violate that property. That sort of upsets us a little bit as an understandability thing more than anything else.
I see. Okay, so I didn't even realize that they both implement the same traits.
Yeah, they both implement exactly the same traits. So it's actually kind of nice from a verification perspective, because it means that we can guarantee that the reference model is implementing all the methods it's supposed to implement. We're not accidentally missing something from our verification. The compiler will check that for us. That's a nice little trick.
And it looks like we have a question from Masanori Misono at the University of Tokyo. So he asks, is Rust a good language for writing specifications? Does it have enough functionalities?
Rust is not a bad language for writing specifications. I wouldn't say it's a good language for writing specifications either. Choosing Rust as a specification language is a sort of a pragmatic choice on our part. We're doing it because our implementation is written in Rust, and we want our specs to live alongside the implementation. And it turns out that Rust has enough of the niceties of a modern language that it's not too bad to write specifications in it. But we're certainly giving something up by doing that, right? We can't write complicated specs with quantifiers in them. We can't write specs that are non-deterministic, for example. And we're giving stuff up by using Rust as a modeling language. And I think, for example, if we were implementing our system in C, and the question was, should we use C as a specification language? The answer is probably not. But Rust has just enough of the nice modern features you'd expect from a programming language that's not too bad to write specifications in it and have them be reasonably concise and yet expressive.
So I'm curious, you mentioned quantifiers. So if you were able to write quantifiers in your specifications, how would you use them? Like, are they something you want to evaluate at runtime? Or are they something that you want to symbolically evaluate with a symbolic execution?
Yeah, it often comes up for us in our how we check crash consistency. You often want to check, does there exist some schedule in which these operations happen that makes this property true or false, right? And we don't have a way to do that besides just brute force enumeration of all the possible schedules. And so you can imagine if you could instead capture that as an actual quantifier, you could do something smarter with a theorem prover or with something else to check those properties without resorting to just brute force enumeration of all the disk states, which is super expensive.
And if you were able to add features to the Rust language to help writing specs, do you have a wish list for that?
Yeah, we've thought about this a little bit. We actually talk in the paper about how we've been working with some of the Rust verification tool developers to sort of figure out what would we need from their tools to make them usable for our verification. And it's sort of like pretty obvious stuff, right? There's no annotation support in Rust, so I can't annotate a function with some predicate or some property that I want it to support. Things like that are relatively lightweight, and that, having spoken to some of the Rust developers, they're interested in supporting. I think the biggest thing that my understanding of these tools, the biggest thing that's a challenge is that kind of the same problem that LLVM has, which is that the developers don't want to commit to an IR. And so if you want to build a verifier based on their IR, that's not really a thing they want you to do, because they want the flexibility to change it. And so we would be an indirect consumer of those changes, but I think that's something we'd be really excited about if we could make progress on the verification tool side to the point where you could build a reliable tool based on those intermediate languages. You're muted, Chris.
Sorry about that. I'm just trying to promote. We have another. Okay, so I'm having trouble promoting here, but I have another question from Reto Ackerman at University of British Columbia. He asks, could you integrate the lightweight verification with Prousty?
Yeah, and that's actually something that we've thought about doing. The way we've been thinking about approaching that question, it's not really Prousty specific, but we've been thinking about sort of carving off parts of our verification problem and that are tractable for a tool like Prousty, and then using that tool just for that piece of code. We talk in the paper, for example, about how we've been doing this for some of our serializers and deserializers, things that actually read data off the disk and check that they're well formatted and stuff like that. Because that code is small and pretty compact and therefore easy to verify, but it's also pretty critical for correctness. We treat data off the disk as untrusted because it might have been corrupted. And so getting that data right is actually super important. And so we've been sort of gradually figuring out what parts of the code we could pop off of our lightweight verification approach and push into a more heavyweight, more strong verification approach.
Okay, and do you have I think we have time for a quick question from Inho Choi. Go ahead.
Hello, yeah. Okay, thanks. We'll ask a short question. I'm Ino from NUS. Thanks for the great talk. And my question is, because you mentioned some gap between your automated lightweight approach and full formal verification in terms of the correctness guarantees. So do you have any potential approaches or ideas to improve the correctness guarantees of this lightweight and automated approach to be closer to the full formal verification?
Yeah, that's a really good question. I think part of the answer is what I was just saying to the previous question about, we're sort of picking incremental components out of our stack and then applying stronger verification tools just to those components, right? So that gets us stronger guarantees about a part of our stack. And then sort of we're also attacking it from the other direction of trying to build better Rust tools that can give us those stronger guarantees while still being automated. So we talk in the paper about a model checker that we built for checking concurrent Rust code, and that gives us slightly stronger guarantees than some other tools would, and sort of scales to the problems that we need. So we're kind of like working on it from both ends in some sense, like building better tools and then also trying to pick components and use off-the-shelf tools for those where it makes sense.
I see. Thanks. Great answer. Yeah.
Okay, and thanks again, James.
Oh, thanks.
And, let's go on to the second talk of the session, which will be